vLLM and llama.cpp are the two names everyone throws around for running large language models yourself, so I put both through 5 head-to-head tests to see which one actually holds up under real load. The biggest surprise in the research, llama.cpp's reputation as free local inference falls apart the moment you put it on a rented GPU, where it actually costs 0.08 TAR to 0.025 per $1,000 tokens in real compute. By the end of this video, you'll know exactly which engine to run, and it comes down to one question about your hardware. Both engines are free, open source software, no license fee either way. vLLM ships under Apache 2.0, llama.cpp under MIT. vLLM's real cost is whatever GPU infrastructure you already own or rent. llama.cpp's compute, community reported, runs 0.08 to 0.05 per $1,000 tokens on a GPU instance. These are two different cost models, not two numbers on the same scale, so this one's a directional tie. Cost, tie, but free only covers the software. Run 10 million tokens a month, and that's $80 to $250, plus another 20 to 40% for egress and storage. My name is Brian, and I spend my time digging through official docs, benchmarks, and pricing pages, so you don't have to sort through 10 open tabs to make this call. Here's where this test gets short. Neither project publishes human evil or SWE bench scores, and there's a simple reason. vLLM and llama.cpp are engines, not models. There's no published figure for either one, because coding accuracy depends entirely on what model you load, not the engine running it. This one doesn't get scored. It's a non-factor in the decision. This is where the split starts. vLLM's page detention and continuous batching were built for one job, keeping a GPU saturated under concurrent requests. At launch, that architecture reported up to 24 times the throughput of Hugging Face transformers, community reported. llama.cpp plays a different game. It's memory bandwidth bound, and it's efficient at it. On dual-channel 3200 Nhz RAM, just 5 CPU threads fully saturate the bandwidth. Push past your physical core count, though, and it backfires. An 8-core AMD chip actually loses performance going from 8 threads to 9. One of the biggest problems I run into when using AI agents is turning their output into YouTube content I can actually use to market my product. That's why this video is sponsored by Subscriber, a tool that helps business owners connect their AI agents to YouTube and market their products without spending 10 hours every week creating content. You can connect Claude or ChatGPT directly to Subscriber. It then analyzes your business, website, and YouTube channel to help you create SEO-optimized video ideas, scripts, thumbnails, and even complete videos that actually match your brand. What I like most is that every week, Subscriber gives me a list of high-potential video ideas I can immediately execute, and it can even help edit videos for me, with or without my face, including videos like the one you're watching right now. It's easy to get started, and you can try Subscriber for free using the link in the description below. Now back to the video. So, vLLM wins raw concurrent throughput. The llama.cpp wins efficiency on hardware that has no GPU to speak of. For this test, the win goes to vLLM, so vLLM takes speed and the scoreboard shifts its way. Stick with me because the last 4 tests are where this decision actually flips. vLLM gives you a direct dial. The max model len flag lets you set an explicit window. 34 to 100 tokens for QN3 or 30B A3B FP8 is the documented example. A llama.cpp configures context through runtime parameters too, but the standard benchmark setup tests at a modest 2048 tokens, and there's no published maximum in the research. vLLM wins this one on both configurability and tested ceiling. Context, vLLM. Community testing has pushed it to roughly 538,000 tokens on 4 H100s, with around 500,000 recommended for stability. llama.cpp's biggest advantage isn't speed, it's reach. It's a C++ binary that runs anywhere a C compiler runs. CPU, CUDA, Metal, Vulkan, ROCm. It also invented gguf, which is now the reference format for quantized local models, letting you split a model across CPU and GPU at once. vLLM covers serious ground too: CUDA, ROCm, TPU, CPU, Apple Silicon, plus a drop-in OpenAI-compatible API with Docker, Kubernetes, and SkyPilot support built in. That API and orchestration story is vLLM's edge. But on raw portability and the format it created, llama.cpp takes this category. Deployment, a llama.cpp. vLLM wins where concurrency and scale matter, up to 24 times the throughput of HF transformers, and a context window that's been pushed past 500,000 tokens. If you're serving many users off one GPU cluster, those two wins are the whole argument. Llama.cpp wins where flexibility matters. It runs on a C++ binary anywhere a compiler exists. It invented the JDUF format everyone else now uses for quantized models. And it ties vLLM on cost since both are free software to start. On the scoreboard, vLLM wins 2 tests, loses 1, and ties 1, with coding left unscored since neither engine publishes it. That makes vLLM the technical winner here. But the scoreboard isn't the real decision. The winner comes down to one question. Do you have the VRAM? If you're running a production GPU cluster with concurrent traffic, vLLM's throughput and context ceiling are worth every bit of the set. Now, on the scoreboard, vLLM wins 2 tests, loses 1, and ties 1, with coding left unscored since neither engine publishes it. That makes vLLM the technical winner here. But the scoreboard isn't the real decision. The winner comes down to one question. Do you have the VRAM? If you're running a production GPU cluster with concurrent traffic, vLLM's throughput and context ceiling are worth every bit of the set. If this helped, the next breakdown on the channel goes even deeper.